Hi, my name is Andrea Wall, and I am the structural engineer and project manager for Spectralite Engineering. With me today is Connie Zhao, our hydrological engineer, Grace Jackson, our environmental engineer, and Alec Myers, our geotechnical engineer. And we are happy to present our final design for the Valparaiso water treatment plant. So in this presentation, we're going to go over the scope of what we were expected to do, our construction cost, and then we'll go into what exactly each of our 4 disciplines designed. So our design scope, as the structural engineer, I was responsible for designing an office building and a process treatment building, which would house all of the treatments needed to treat the water coming in and then going back out to the city. Our geotechnical engineer was responsible for the foundation design for both of the buildings, along with the new water storage tank that we would be sizing and putting onto the site. Our hydrological engineer was responsible for all of the stormwater management practices, which would help keep flooding at a minimum on the site, along with the pumping and distribution line from a new well field to the process treatment plant, and the sizing of a new water storage tank. And then our environmental engineer helped the hydrological engineer in selecting the water supply source, and then designing all of the process treatments to treat the water coming in and would be housed in the process treatment building. So this is the site plan as it currently stands. This is the one of 2 water treatment plants within Valparaiso. It is the smaller one, if I'm remembering correctly. And currently there's a process treatment building here, and then 2 water storage tanks here. So our design estimate, there's each of the main components of all of our designs, and then the final cost estimate was about $25 million. So with the structural design, in order to do the structural design, I had to first evaluate, okay, what are the loads onto the buildings? This includes the weight of the building itself, everything going into the building, so like chairs and tables in terms of the office building, the weight of the green roofs, which our hydrological engineer will talk about, and then what effects any of the wind will have, as Valparaiso is a pretty windy city. And then I had to take all of that, and I used a 3D modeling program called RISA 3D to create models such as this one right here. And I could use that to help me design and choose all of the member sizes. And then from there, I would do hand calculations to verify that, and then do connection designs such as these 2 in order to connect all of the members together safely. These are just some of the considerations. In the design, one thing I had to keep an eye on was the deflections of all of the members, as you don't want a building that bows too much, because that's 1, not safe, and 2, even if the building does support it, people will not feel safe being within a building where the floors aren't level. So here's the design of the office building. It is a 2-story, 6,000 square foot office building. And there is 151 steel members that go into it. This is the framing plan for the floors of the office building. The beams are the ones going side to side, and the girders up and down. And then within the office building, I had to allow space for a general office for all the staff, a computer lab, the file storage room, a manager's office, a lab, because it's very important that all the water coming in is tested, all the water going out is tested, so we are sure that everything we're dosing and everything we're doing is ensuring the best quality water. On the 2nd floor, there is a conference room, a break room and kitchen, and a balcony, so all the staff members, when they're on their breaks, they can go, when it's nice out, outside and relax and just chill. And then there's the process treatment building. This building is 49,150 square feet. It has 293 members because it is so much bigger than the office building. And then there's the 3D model right there of what it may look like depending on what an architect decides to do with the outside. Here's the framing system for the process treatment building. The spacing between beams and columns isn't as normal for the This is the framing plan for the process treatment building. The spacings aren't as normal as the office building because the entire process treatment building was designed around what Grace had designed for the processes. So each column is placed in order to ensure workers can get around everything and access any of the processes that need to be fixed. Anything that needs to be replaced can be taken out, put back in, and so on. And here is the layout of that. Grace will go more into this in detail in a bit, but it would start rapid mix tanks down here, which are these two, then flocculation, sedimentation, rapid sand filtration, and then a UV, fluoride, and chlorine treatment. And now I'll hand it off to Alec for the geotechnical.
So just a brief overview of what I was tasked to do with. First, I had to review and analyze the on-site soils for our site. And then I had to research different foundation types for the buildings and the water storage tank, and ultimately design these foundations. So as you can see, here's our soil boring log on top of the site plan. So our office building is going right there on top of A1, so that's the properties I used for that. A3 is where the water treatment building is placed, and A2 is the new water storage tank. So obviously I use the soil properties for their respective buildings. So the different foundation types that I researched throughout the year was a spread footing, a strip footing, and a pile foundation. The spread footing is just a basic square foundation placed directly under a column. The strip footing is a continuous strip of concrete placed directly under a load-bearing wall to help distribute the larger load over a larger area. And then the pile foundation is used for an extremely large load to help distribute that load all the way down into the deeper soil layers, which are much stronger. In all of these designs, the two main constraints was that it had to be under an inch of settlement and have to have a factor of safety of above 2.5. So for the building designs, we decided to go with a spread footing foundation, which was a 7x7 foundation reinforced by 6 number 8 bars. Now, as you can see, the settlement was 0.7 inches and the factor of safety was 7.4, so it was a very safe design. And of the three alternatives, it is the most cost-effective design, so that is why we chose this one. Now for the water storage tank, there weren't as many alternatives. It was either a concrete ring wall or a crushed stone ring wall. For the design of these two different foundations, they are very similar, so I ultimately decided to go with the concrete ring wall, which is much like the strip footing. It's just a continuous strip of concrete placed directly under the water storage tank diameter. And as you can see, once again, the settlement is under an inch and the factor of safety is above 8.9, or is above 2.5. So it is a safe design reinforced by 5 number 8 bars. And then I'll give it to Connie.
My name is Connie. I'm the hydrological engineer from Spectrolite Engineering. My responsibility for this project is to design the distribution route from the water source to our new water treatment facility, and also design a new water storage tank, and also do the stormwater management practices. All my design criteria are from the City of Valparaiso Stormwater Technical Standards Manual. One thing that I did too is to do the water quality control. This picture shows us that why it's important to do this. As we can see, when it's raining, the rainfall runoff will go through the surface, and the runoff will catch up the pollutants come from the garbage and also the traffic, so it will cause the pollution of the water. So we need to calculate the water quality volume, which is the storage needed to capture the pollutants and treat them from the first 1 inch of the rainfall runoff. So to treat this water quality volume, we need to design the water quality best management practices. There are a lot of stormwater BMPs, for example, like the sand filters, the rain gardens, green roofs, and also the permanent pavement. For our project, we use the green roof as our main element to treat the water quality volume. The reason why we chose this is because our building took a lot of space on our site. So it's not possible to have a huge sand filter or a huge rain garden to treat the very big water quality volume, which is 7,885 cubic feet. So the green roof became to our best alternative for the water quality volume. The total area of the green roof is 52,100 square feet. And on each green roof, we'll have a 25 square feet roof access area for the maintenance people to get on the roof. And the soil type that we chose is the loam soil. The first layer, the top layer of the green roof is the vegetation, and then there's 3.5 inches growing medium, so the water will go through this soil layer and to the drainage layer, which can storage the water. And under that, there's an insulation layer and the roof membrane layer, and to protect the roof from the water. The total volume that the green roof can work on is 7,035 cubic feet. We designed a rain garden as an additional element to treat the water quality volume. The rain garden is designed to treat 1,000 cubic feet of the water quality volume, and so we have a size of 5,070 square feet. The rain garden will have a grass filter strip as 5 feet, and the side slope is 3:1. In order to control if there's a really huge heavy storm happen, so we need emergency overflow weir. The weir size is 11 feet. Another thing that I did too is to control the flood. The flood control is work for reduce the runoff on the surface. This picture is what if we don't do this well, there will be flood on the surface. We don't want that. So based on the city manual, our design period is 24 hours, 100 years rainfall, and the precipitation depth is 8 inches, and the calculated flood control volume is 2.19 acre feet. To treat this volume, I designed a wet detention pond. The wet detention pond has 6 feet in depth, and the permanent pool surface area is 8,090 square feet. The wet detention pond will have a 3:1 set slope and a 1 feet freeboard. Because of the increasing population in the city, we need to storage more water to support the resident and the water and the fire departments. So we will have a new water storage tank. Our current water storage tank can storage 2 million gallons of water, and our new one will storage 2.5 million gallons of water. The new water storage tank has a radius of 40 feet and the height is 70 feet. Our water resource is come from the groundwater, and we will have a new well field located between the 400 East Road and the 200 North Road. Our environmental engineer will explain how did we get this later. So we will have a total of 6.4 miles galvanized iron pipeline to get the water from our new well field to our water treatment facility. The pipe will has a diameter of 18 inches, and in order to provide enough energy to transfer the water from new well field to the treatment facility, we will put 3,000 horsepower wheel pump on the new well field. Now I'll pass to the environmental engineer.
So like Connie talked about a little bit, we looked at water sources, and she showed you the pipeline for getting that water to the treatment plant. But just a little bit of information about how we selected our water sources. So we designed the project to have a design life through 2046. That includes the design and construction phase, and then taking us through a 25-year design period. And then through population data, as well as analyzing growth of industry and businesses in the city of Valparaiso, we ended up with an average daily of about 7 million gallons per day and a peak daily demand of about 16 million gallons per day. So that peak demand reflects the hours when a lot of water is in use, so people are home, people are washing their dishes after dinner, people are taking showers. So there's hours of the day when a lot more water gets used, and there's hours of the day when people are all asleep and a lot less water gets used. So that's what that number is. So ultimately, we decided to go with a groundwater source. So we also looked at surface water sources like Lake Michigan, Kankakee River, and Flint Lake, which is next to the site. But groundwater is already in use in Valparaiso, and so we looked at how we can expand some of that groundwater and have a few more wells to reach that capacity. So these green boxes on the screen indicate the current well fields in Valparaiso, and there's currently 2 by the Valpo Airport, and one of those is being decommissioned in the coming year. So there's currently 20 wells. Some of those are being decommissioned, and then we selected a location for a new well field in order to reach the demand needed for that design life through 2046. So then looking at the water quality of water coming from the wells, we had to identify what contaminants we had to treat the water for. So there's 2 primary contaminants, and primary contaminants are ones that pose a risk to public health. So that's antimony and thallium. They're typically heavy metals, and they are federally enforceable by the EPA. So the EPA has set forth standards, and you have to continuously test for these contaminants and make sure that they aren't present in the water that's being distributed to the public. And then there are also secondary contaminants present. So these don't pose any risk to public health. The water is still potable, but it's not palatable. In this case, in all instances, these secondary contaminants can cause discoloration or taste differences. And so we're also treating for iron, manganese, and total dissolved solids. Total dissolved solids are things like calcium and magnesium, which cause hardness. So if you've ever seen like calcium buildup, that like white buildup that comes, that is common with groundwater. It's a common complaint with Valpo water that they haven't removed enough of that hardness. And so we're looking to bring that down. And then the MCL is maximum contaminant level. So that column is the regulation. The measured is what's currently measured through the Valpo groundwater. And then this total dissolved solids number, the MCL is 500, but we wanted to get ours to be below 400, and it ended up being about 320 when we finished the treatment. So the big part of my project was looking at alternatives for water treatment and then selecting an alternative to design. So we ended up going with a coagulation and flocculation setup, and I'll go into each of these portions in more detail on the following slides. So this is the overall process treatment diagram. So the water is going to begin at the well fields. It's going to go through coagulation rapid mix, then it's going to go through the flocculation sedimentation tanks, then through rapid sand filtration, and then pass through storage, and on its way to being distributed, go through disinfection and fluorination. So beginning with coagulation and rapid mix, the purpose of coagulation is to add a chemical to the water that has a positive charge, and then it causes a reaction with contaminants in the water to form a precipitate, and to ensure that the chemical distributes all the way throughout the water and comes into contact with those contaminants, you put it through a rapid mix tank, which is designed here. And some of the big considerations for that are the detention time within the rapid mix, so that's about 5 seconds, and then the dosage, and the dosage impacts how quickly it will flocculate, and then also the level that it will remove contaminants. So then it passes through the flocculation basin. So this ensures that the different precipitates that were formed through the chemical reaction touch each other to form larger, we call them flocks, that become heavier so that in the following step, they will sink to the bottom of the tank. And so you keep the water mixing through this, but one of the big considerations is making sure you mix slow enough that you don't shear any of the flocks or cut any of the flocks, because the goal is to make those large, but to keep it mixing so that they come into contact with one another. So this is the overall design of the tanks. It goes through 3 different rotation paddles to the end of the tank, and then this tank is connected to the sedimentation basin. And so this is where you have the larger flocks that have become heavier, and you want to allow those time as they process through this basin slowly to sink to the bottom of the basin and form a sludge at the bottom that can be removed. So overall, you want to ensure that you have a length that is suitable to do that. So that's why the tank has a length of 160 feet. And then you want to have a detention time that will also suit that. So the detention time overall for the tank is 3 hours that the water will take to pass through. And then rapid sand filtration removes any of those remaining particles that maybe weren't heavy enough to sediment out of the process. So speed's also a huge factor with this, making sure that the speed is right, that it doesn't process too fast or too slowly, because you also have to keep water circulating to the public. And so we chose a dual sand filter. There's coal on the top layer, and then sand, and then there's gravel at the bottom of the tank that the water passes through on its way out. And then another big part of rapid mix is that you have backwashing, so you pass water through the tank in addition to what you're treating. And so that's why you can see here, this is the tank, and it's built in a cell, so there's a tank on either side, and then there's a channel through the middle of the tank that passes the water through, and then there's all these troughs coming off of it, and so the water comes out from those troughs and passes through the tank. And then finally, on its way to distribution, you have to disinfect the water. So we chose as our primary disinfectant UV, and so it passes through a machine that passes UV rays through the water. And then our secondary disinfectant is chlorination, which is pretty standard. UV is kind of the up and coming technology that's becoming more and more popular. And then finally, it has fluorine added to the water because the city of Valparaiso has a mandate for fluorine levels. Fluorine is already present in the water at about 0.6 milligrams per liter, so then we're just adding the remaining amount to get it to that level mandated by the city. So overall, this is another summary of the process treatment diagram, and that is the conclusion of our presentation. So at this time, we welcome any questions that you have.
You talked about the water demand. You said about this. Does the city of Valpo include fire protection water in that demand?
Yeah, the fire protection water is a factor in that demand, and that was a big factor in the selection of the water storage tank that Connie talked a bit about, because there's a fire protection manual that mandates how much extra reserve water you should have in case of fire.
Thank you.
Spell my name wrong. Cool.
Yeah, about 6 inches below your mouth is perfect. You guys are all able to just put it kind of as low as you can toward that top button. Yeah, perfect. Guys, be careful of this button, because if you tap it, so make sure that light's green. Okay. And then the first speaker will pass to the third speaker, the second will pass to the fourth.
Okay, sounds good.